Okay, so let us continue chapter 8. We were talking about the different type of castings. One of the types is squeeze casting. Squeeze casting consists of a combination of casting and forging processes. If you remember when we talked about forging processes, they consist on applying a certain pressure, and we'll see this into details in future chapters. We'll discuss forging techniques in which a molten metal is poured into a preheated lower die, and the upper die is closed to create the mold cavity after solidification begins. Now, in this process, it differs from the usual closed mold casting, in which die halves are closed before introduction of the molten metal. So here, one of the main difference is that in this case, we have that die halves are closed before the introduction of the molten metal. However, in the other case, we have the pouring part, then we close the die, and we compared to conventional forging, pressures are less and finer surface details can be achieved. So when you combine casting and forging, then the pressures will be lower than the pure forging technique. Now, another type of casting is semi-solid metal casting, and it's a family of net shape and near net shape processes. This means that we don't have a lot of waste in these processes, and it's performed on metal alloys at temperatures between liquidus and solidus. If you remember, when we consider alloys and the variation of temperature when during the pouring part, we said that we have a range of temperature where melting will take place, where solidification will take place. And then in this case, we say that we are performing the casting with the alloy in a mixture of solid and molten metal. This is called the mushy state. To flow properly, the mixture must consist of solid metal globules in a liquid. So we can have this, but we should ensure a certain fraction of liquid to facilitate the pouring process. And it can be achieved by stirring the mixture to prevent dendrite formation. So solid will just should be in small parts and not in big parts in order to allow the casting operation to take place. Now, semi-solid metal casting represents several advantages, that it can allow the formation of complex part geometries, and we can manufacture thin walls, which is a good characteristic. In addition, it allows us to have close tolerances and to avoid the porosity effect. So we can reach zero or low porosity, resulting in a high strength of the casting. All of these processes are illustrated in the YouTube links I provided you. So I encourage you to watch them, because you will see in reality how these processes are happening. Another type of casting is centrifugal casting. Centrifugal casting, and as the name indicates, it will rely on certain rotational effect when the casting process is done. So this is a family of processes in which the mold is rotated at high speed. So centrifugal force distributes molten metal to outer region of die cavity. So under the effect of rotation, you are able to reach far regions, and this will allow to get more complex geometries. Now we have several types of centrifugal castings. First, we have the true centrifugal casting, the semi-centrifugal casting, and the centrifuge casting. Let us see what is the main difference between these types. To start with, for the true centrifugal casting, the molten metal is poured into a rotating mold to produce a tubular part. So in general, whenever we have a tubular part geometry, we can use the true centrifugal casting. In some operations, mold rotation will start after pouring rather than before. And the different parts that we can manufacture using this type of castings are pipes, tubes, bushings, and rings, all of them having a tubular geometry. And the outside shape of casting can be round, octagonal, hexagonal, but the inside shape should be perfectly round. So you have a freedom for the geometry of the outer part, but for the inner part, in this process, it should be perfectly round because of the symmetry of radial forces. Now you can see here the setup of true centrifugal casting. As you can see, we have driver rollers and the mold in between. So due to the rotation of the driver rollers will drive rotation of the mold. And then after the pouring step, the rolling, even during the pouring step, you can start to have the rotation. And this will allow you to create the tubular parts. Now, what about semi-centrifugal casting? So in centrifugal, in this system, the centrifugal force is used to produce solid casting rather than tubular parts. So when we talk about tubular parts, in general, the thickness is not very large. If you have to produce like a rotating geometry, but you should have a solid casting, so you don't have a hole inside, you need other techniques. So in this case, we need to use risers at the center to supply feed metal, and the density of metal in final casting is greater in outer sections at center of rotation because of this effect that you have the formation of the outer part first, and at the end you have the center part. This will create a certain density variation within the casting. Now, in general, this type of casting is often used on parts in which the center of casting is not is machined away. So because the characteristics at the center will not be as good mechanically as the outer characteristics. So therefore, when we use this system, in general, we eliminate the portion where the quality is the lowest. This is widely used to produce wheels and pulleys. So you still have, you produce first as a full solid, and then you remove the weak part and by using machining techniques, so you can produce objects like wheels and pulleys using this type of casting. Another type, this figure illustrates the semi-centrifugal casting. So as you can see, in this case, you have the cup and drag parts as usual. You have a rotating table which will create the centrifugal forces. But the difference here is, as we said, it's a full part. You don't have just a thin part like in the first type of casting. And at the end, in case you want to, if you find the center part weak, you can remove it. Or depending on your application, if you don't have to ensure very high mechanical properties at the center, you can keep it. Now, the last type is centrifuge casting. In this system, mold is designed with part cavities located away from the axis of rotation. So molten metal will be poured into mold and distributed to these cavities by centrifugal force. This type of casting is used for smaller parts, and the radial symmetry or part is not required as in centrifugal cast method. So the main difference between the first type and this one is that we don't have to maintain for the inner part a perfectly round surface. Okay, so this is the main difference between the first type and the third type. We are able to produce, if you want, tubular parts, but no need to ensure a round part at the internal surface. And this is the figure showing us the centrifuge casting process. So as you can see, you can produce thin parts, and you have more flexibility in geometry in this case, because you don't have to ensure perfectly round surfaces from inside. Now, as I told you, you are not responsible of furnaces for chapter 8, so we'll skip that. Okay. Now, whenever we do as a casting process, we need to transport molten metal, and molten metal will be at very high temperature. So we should have we should use specific material to transport molten metal. As what is used is ladles, and we have two common type of ladles. Sometimes when we have very large temperature, you have the two-man ladle. So you have two mans that will transport the ladle, and you have like here you can ensure a forest distance between the worker and the ladle. And in case of lower temperature applications, you can just have one worker transporting the molten metal, and this is a ladle used. It's called crane ladles. So these are the main two types used, and depending on the temperature of your metal, you can decide which one to use. Now, we have several steps to do after solidification of the cast. So as we mentioned before, whenever you use, let's say, a closed mold, you have several parts that should be trimmed at the end. So the risers, the channels for pouring. So you'll have remaining material when you open your mold, and you should trim these parts in order to get your final desired cast. So the first step will be the trimming. Also, you should remove, in case you have a core, you should remove it. You should do some surface cleaning, because you might have some, if you are using, for example, sand casting, you might have some sand particles adhering to the cast. The inspection is to make sure if you have any defect or anything that can be fixed before getting your final product. So you might repair if required sometimes. And also we can do heat treatment to enhance the mechanical properties. We'll go over these different steps after solidification in detail. So first, let us talk about trimming. Trimming consists of removal of sprues, runners, risers, parting line flash, fins, chaplets, and any other excess metal from the cast part. So as we mentioned, all parts that are related to the cavity but not forming the final cast should be removed. Now, sometimes it will be easy to remove them. If you have brittle casting alloys, yeah, then and when cross sections are relatively small, so appendages can be broken off easily. Otherwise, you might need more complex techniques to remove these parts, as hammering, shearing, hacksawing, band sawing. We'll go over the majority of these processes in this course. We can use also abrasive wheel cutting or various torch cutting methods. So it depends if you want on the material, the cast. If you have a material that is characterized by a high hardness, so you might need more complex technique and cutting techniques to remove the unuseful parts. Now, concerning the core, if cores has been used, also they must be removed. Now, most cores are bonded and they often fall out of casting as the binder deteriorates. So in general, we use binders to form cores, and after the casting process that they will deteriorate, so you can remove the core easily. In some other cases, you can just remove them by shaking the casting, either manually or mechanically. And in rare cases, cores are removed by chemically dissolving bonding agent. So in case the bonding agents will not deteriorate without any external action, we can use chemical reactions to remove them. And solid cores must be hammered or pressed out. Now, another step is after the casting is the surface cleaning and inspection. So as we said, you might have some particle of sand adhering to the final cast. So we should remove sand from casting surface, and otherwise we should enhance the appearance of the surface. Now we have several cleaning methods that can be used, including tumbling, air blasting with coarse sand, grid, or metal shot. So sometimes we have a jet of air that we move through the cast and with high pressure in order to remove dirt and remove any sand particle adhering to the cast. You have other techniques also as wire brushing, buffing, and chemical pickling. Now, surface cleaning is most important for sand casting because sand will adhere in a certain way to the cast. So you need to do separation between the sand particles and the final cast. And defects are possible in casting, and inspection is needed to detect their presence. We'll see together what are the different type of defects that we can encounter in casting processes. Now, concerning heat treatment, we already mentioned before that a heat treatment can enhance the mechanical properties of a cast. So, castings are often heat treated to enhance their properties. The reasons for heat treating includes subsequent processing operations such as machining. As I told you, in general, for sand casting, for example, you have low accuracy. So in case you have an application with restricted tolerances, it's not enough to do sand casting. You should continue to process and do some machining operation to enhance if you want, the surface finish of your cast. And another objective of heat treatment is to bring out the desired properties for the application of the part in service. So as we have seen, heat treatment can, if we have talked about the quenching process before, so you can create better mechanical properties for the external surface, etc. Now, concerning the defects, we'll talk about what are the different possible defects taking place and how we can try to avoid them. So there are several opportunities for things to go wrong in a casting operation, resulting in in quality defects in the product. The defects can be classified as follows. You have general defects that are common to all casting processes, and you have some defects that are related specifically to sand casting process. We'll start first by describing general defects. You have the first type of defects is a misrun defect, okay? And we already talked about this. So we said that during the pouring operation, we should have a temperature much higher than the melting temperature in order to be able to achieve, if you want, the pouring step and without solidification before reaching the extremities. So in case the melting temperature was not high, the pouring temperature was not high enough, as you are pouring, you might have start of solidification before reaching the extreme zones. One of the possible solution to this defect is the use of risers. So you can use of risers near far extremities, which will ensure continuous supply of molten metal. But also here we have the risk of blocking effect. So in case you need also to supply molten metal to other regions, this can lead to some blocking effect. So you might need to use several risers in this case. So to avoid such defects, we should study the geometry of the cast and decide on the number of risers to use. In addition, we can use a larger pouring temperature. So we talk about misrun when a casting has solidified before completely filling the mold cavity. Another type of defects is the cold shot. So we already mentioned that near walls, okay, we have more heat transfer and we can have solidification that is faster than the other parts. So here, for example, you have two portions of metal flowing together, but there is a lack of fusion due to premature freezing. So here you have the molten metal will be divided into these two regions, but this region is more critical because you have a thinner section here, and you have heat loss through the environment and through towards the external part and towards the core, which will cause rapid freezing of this part, and this might lead to lack of fusion. So this is what we call the cold shot. Now, Another type of defects is also related to cold shots is when you have metal splatters during pouring and solid globules form and become entrapped in the casting. So and you can see this specifically close to walls. So as usual, because the fast freezing effects, this might lead to formation of globules that will be entrapped in the casting. Another type of defects is shrinkage cavity. So also, as you can see, the majority of defects are close to walls because of the fast solidification near the wall, which will not allow molten metal to reach subzones. So we can observe shrinkage cavity, which is depression in surface or internal void caused by solidification shrinkage that restricts amount of molten metal available in last region to freeze. So this will lead to the formation of a shrinkage cavity. And of course, the riser is one of the solutions for this because we will put the riser in zones close to the to parts where we can still supply molten metal until the complete solidification. Now, another type of casting defects is sand blow. It consists of balloon-shaped gas cavities caused by release of mold gases during pouring. During the pouring process, sometimes you have, due to turbulence levels during this step, you have formation of gas bubbles. And in case you don't have a riser that will continuously supply molten metal, these gases will be trapped during the solidification process, and you will end up with some small holes within your mold. So you can see that riser is very important because it can present a solution for the majority of these defects, but sometimes the design of riser is complex and we might need to use several risers instead of just one. Another type of defects that is specific to sand casting is pinholes. So pinholes consist of formation of many small gas cavities at or slightly below the surface of casting. It's very similar to previous defect we discussed, which is related to during pouring step, you have formation of gas bubbles, and these gas bubbles will be trapped especially you can see them near surface of castings because of the fast solidification of these parts. Now, another defect that is characterizing sand casting is penetration. You know that sand is not very hard or solid. So, if you have a molten metal characterized by a high fluidity what can take place is that the molten metal can penetrate into sand mold because sand is not very rigid, and this will cause casting surface to consist of a mixture of sand grades and metals. So as you can see here, you have some penetration effects which will alter the surface characteristics. So of course, at the end of the process, you should trim this part. Now, another type of sand casting defects is mold shift. So as the name indicates, you will have a certain shift between the two parts. So you remember that cope is the upper part and drag is the lowest part. In this type of casting, in sand casting, you might have some shift between the parts, which will cause a certain asymmetry in your final product. So a step in the cast product at parting line can be caused by sidewise relative displacement of cup and drag. Now, what about inspection methods? So we said at the end of the casting process, we should perform some inspection. in order to detect some possible deficiency in the cast process. One of the possible inspection is just the visual inspection to detect some obvious defects such as misruns, cold shots, and severe surface flaws. In addition, we can perform dimensional measurements in order to check if tolerances required are achieved. Uh, and in case it's not, we should use extra machining in order to enhance the surface finishing of the final part. Now we can do several other type of tests. You can do metallurgical tests to test the quality of your the properties of your of the components constituting your cast. You can do some chemical tests to check the chemical structure. You can have many other physical test, which will all test the quality of the cast metal to make sure that the required and desired properties are achieved. If not, you can try to enhance if you want the setup or change, let's say, the pouring temperature, change, for example, let's say use, sometimes we use, we alter the composition of the cast metal in order to have better properties at the end. So we use alloys in this case. Now, what are the metals used for casting? We have several, for most commercial casting, we use alloys rather than pure metals because as we said, with alloys we can, if you want, to play more with the properties and we can have better final mechanical properties of our system. In addition, alloys are easier to cast and properties of product will be better. Now we have several casting alloys that can be used, and we already discussed at the beginning of the course ferrous and non-ferrous alloys. So both can be used in casting. Now, cast iron is one of the most important of all casting alloys, and the tonnage of cast iron castings is several times that of all other metals combined. Now, we have several types of cast iron, including gray cast iron, white cast iron, alloy cast iron. So all of these types can be used, and they are characterized in general by typical pouring temperatures up to 1,400 degrees. And the specification of the pouring temperature will change depending on the composition of the alloy. Now, concerning ferrous casting alloys, the mechanical properties of steel will make it an attractive engineering material. It allows us to create complex geometries, making casting an attractive shaping process. We might fight some difficulties when casting steel because the pouring temperature is relatively high, so we need to have more safety factors, and we need to ensure that the mold can sustain such high temperatures. So at such temperatures, steel will undergo oxidization, so molten metal must be isolated from air. So we should make sure to not have to not have, if you want, a leakage of air to avoid this process. And in addition, molten steel has relatively poor fluidity, so which will make the pouring step more complex. Now, concerning non-ferrous casting alloys, one of the possibility is to use aluminum, which is generally considered to be a very good metal for casting. It's characterized by low pouring temperatures due to low melting temperature. The pure aluminum is characterized by a melting temperature of 660 degrees, and it represents several properties that might be desired. So it has lightweight, and the range of strength property can be affected by the treatment, by heat treatment process. In addition, it's easy to machine. Now, another possibility for non-ferrous casting alloys is the use of copper. That includes bronze, brass, and aluminum bronze. The properties of these alloys will allow to do resistance for corrosion. It will give an attractive appearance for the casting and good bearing qualities. Now, concerning the limitation of using copper alloys is the high cost of copper, and it can be used in several applications as pipe fittings, marine propeller blades, and pump components, in addition to ornamental jewelry. Also, another type of non-ferrous casting alloys is using zinc, which is also an alloy characterized by good properties for casting, and it's commonly used in die casting involving pressures, high pressures. It's characterized by a low pouring temperature due to low melting temperature, and for pure zinc, the melting temperature is around 419 degrees. It represents good fluidity, which will make the pouring process easier, and even it can reach extremities of the cavity without problems. And now it represents as properties low creep strengths, and so casting cannot be subjected to prolonged high stresses. So in this case, we should make sure that we don't exceed the allowable stresses to not have creep, to not have creep and failure of the cast. Now, concerning the product design considerations, so first we should have geometric simplicity. Also, casting can be used to produce complex part geometries. Simplifying the part design will usually improve the casting process. Yani you can try to simplify as much as possible the geometry, as long as, of course, you are not deviating from a lot from the final design. Avoiding unnecessary complexities will simplify the making the mold. Sometimes we can then use a permanent molding process instead of expandable, so it will have lower costs. We can reduce the need for cores sometimes if we just do some modifications, as we'll see together. We can improve also the strengths of the casting. Let us see what are some of these product design considerations. So we should try to avoid corners. 90 degrees angles are not desired, because these zones will be critical, and you know, it's hard, it's not easy to have to manufacture sharp corners. So sharp corners and angles should be avoided, since they are sources of stress concentrations and may cause hot tearing and cracks, which will lead to a failure of the final product. Now we have generous fillets should be designed on inside corners, and sharp edges should be blended. If you remember, we talked about using of fillets, and these fillets will allow us to produce certain curvature to avoid these corners. Now, let us see an example on how we can alter the final design in order to avoid such problems. For example, in expandable mold casting, draft facilitates removal of pattern from mold. So you can do like a draft of 1 degree or 2-3 degrees, depending on the application, to facilitate the removal of pattern. We'll see this in a figure. So, and the value of draft will depend if it's an expandable or permanent mold. An expandable mold where where you will destroy the mold at the end, it's fine if you just do 1 degree of draft in sand casting. However, in permanent mold casting, because you will be you need to use several times the mold, then you can use a draft of up to 2 to 3 degrees in order to facilitate the opening of the mold. So let us see in a figure how this will take place. So you can see here that whenever, let's say you want to remove the mold at the end, doing a certain draft will facilitate the removal process instead of having just a straight line. So this will allow to remove the cup and drag from each other in a simpler way. Now also we can use some if you want strategies. For example, here in this figure, we are eliminating the need for using a core by just doing a redesign for the cup and drag parts. So if you want to have these internal surfaces, which are relatively little bit complex, you need to have a core to create this internal shape. And if your application allow you to disregard these parts. And it depends on the restrictions you have. If you say these parts are not very useful, what if we can remove them? Then you will not need to use a core anymore. You can just extend the drag part in the cup part like this. And then when you open your mold, you can when you separate cup and drag, you will just have your final part without the need to add any core. So sometimes you can simplify your design in order to facilitate your casting operation. Now, concerning the tolerances, we already talked about the tolerances, and we said that in some casting process, it might not, we have large tolerances, so we can, in this case, we might use machining after. So dimensional tolerances are related to surface finish. Dimensional accuracy